Jason Squinball. You know, I really love musical relationships. At its very essence, music is essentially organized sound. And in order to have music, we have to have relationships. You see, one tone of music, one sound, doesn't really constitute music. We need at least two sounds in order to have a relationship and to put the music in context. In a very broad sense, we can generally identify two main types of relationships in music. The first type is the relationship of musical space, and the second type is the relationship of musical time. Musical relationships in space deal with the distance between pitch. In the relationship of musical space, we can have very short distances or we can have very wide distances. We can organize the space between sounds linearly in the form of scales or intervals, or concurrently in the form of dyads, triads, or chords. In the same way that our musical space relationships can be linear in the form of scales or concurrent in the form of triads and chords, so too can our relationships of musical time be both linear in the form of melodic rhythms or concurrent in the form of rhythmic harmony. We often call concurrent form of rhythm polyrhythm, as it denotes multiple rhythms occurring at the same time. I'll use the term polyrhythm throughout this presentation. While Western classical music has primarily focused on the development of musical space, other music cultures have placed more emphasis on the development of musical time, especially polyrhythm. A great deal of West African traditional music and music of the African diaspora is devoted to the exploration of polyrhythm. One of the most common examples of polyrhythm is the occurrence of two sounds and the occurrence of three sounds within the same space. Here is an example of the polyrhythm 2 against 3. While this is probably the most common polyrhythmic relationship, it is certainly not the only one. We have a vast number of polyrhythmic relationships we could explore. However, today I'd like to take a look at 2 against 3, 2 against 5, and 3 against 5. Here's the 2 against 3 polyrhythm one more time. This is what the 2 against 5 polyrhythm sounds like. And this is what 3 against 5 sounds like. These polyrhythmic relationships probably developed naturally within certain music-making societies. However, just as we have developed a theory for composing and analyzing scales and chords, we also have developed techniques for composing and analyzing polyrhythmic relationships. One such way of creating and analyzing polyrhythm is in using Euclid's algorithm. The primary goal of this algorithm is to equally distribute a smaller number of occurrences over a greater number of places. While there's not enough time to go into a full explanation of Euclid's algorithm here, when we apply it to common polyrhythmic relationships, we're able to produce a vast number of common rhythms found within traditional musics around the world. For example, we can take 3 musical occurrences and divide them into 8 spaces of time. In doing so, we start by putting 1 space of silence in between each occurrence of sound. But you'll notice we have 2 left over. We take those 2 and distribute them again in between the units of sound and space, so that we have a sound with 2 empty spaces, another sound with 2 empty spaces, and finally the last sound and the last space. This produces an extremely common rhythm found throughout the world music traditional cultures. In music technology, we can utilize music sequencers to calculate the same Euclid algorithms to produce our polyrhythmic relationships. Here is an example of the 2-3 polyrhythm using a Euclid algorithm sequencer. This is an example of the 2-5 polyrhythm. Here is an example of 3 against 5. We can also combine 3 or more groupings to create even more complex relationships. Finally, here's an example of 2 against 3 against 5. While these polyrhythmic relationships are interesting on their own, in order to use them in more developed compositions, we need to understand 2 concepts: the density referent and the least common multiple. The density referent is the fastest unit of time that a piece of music or a song is based upon. This helps us to establish a steady and equally distributed beat. In musical terms, we usually use 16th notes, 8th notes, or quarter notes in order to represent the density referent of a polyrhythm. If each of our rhythmic time relationships moves at the same density referent and the same tempo, they should all line up together. In order to have successful polyrhythmic relationships, we also need to be able to find the least common multiple of our time relationships. This will allow us to know how many time units it will take for the pattern to line up or begin again. This is relatively simple if we're using 2 small numbers. We know that the least common multiple of 2 and 3 is 6. The least common multiple of 2 and 5 is 10, and the least common multiple of 3 and 5 is 15. It gets a little more tricky when we start to combine 3 or more time relationships. For example, in creating the polyrhythmic relationship of 2 to 3 to 5, we would need to know that the least common multiple is 30, which means our pattern will not line up again and start from the beginning until we have 30 pulses of the density referent. Notice that it takes 30 spaces of time, or according to the density referent, 8th notes, in order for our polyrhythm to come back around and all match up at the top. Schillinger, in his theory of rhythm, also comes to the same polyrhythmic results using a graphic approach. This graphic approach allows us an easier way to visually represent the density referent and show the least common multiple. In our example here, you'll see that we have 30 spaces of musical time. The red line divides up this space into 2 parts of musical time. The blue line divides the space into 3 parts of musical time, and the green line divides the space into 5 parts of musical time. This final black line shows the results of all 3 polyrhythms when paired down together. This is going to be important as we develop our musical composition. Schillinger takes our understanding of polyrhythmic relationships to the next level by creating ways of developing and expanding these polyrhythmic relationships, ultimately using them for musical composition. Schillinger presents many different ways to develop and expand these polyrhythmic relationships. The composition I was playing at the beginning of this video utilizes a few of his techniques. I'll break them down for you here. In my first clip, I have a Euclid algorithm sequencer. That's sequencing 2 against 3 against 5. In my next clip, I have 3 polyrhythmic sequences. 2 against 5, 3 against 2, and 3 against 5. You'll hear them in succession. In my next clip, I'm using a Schillinger technique called fractioning to create a sense of symmetry and extend one of my phrases. I'm actually using a 6-to-5 polyrhythm, which is a derivative of the 3-to-5 polyrhythm, just for a little bit more contrast. In my next clip, I use a Schillinger technique called balancing, which extends the phrase and gives it a nice sense of ending. I use it at 1 density referent, first time, and then I cut that density referent in half and play it twice as fast. See if you can hear it. Do you remember the 2 against 3 against 5 polyrhythm that I showed in a graph on the board? Well, this next clip uses a Schillinger technique to put a linear rhythm together based on that 2, 3, 5 polyrhythm. The final Schillinger technique I use is to take the factors of 2, 3, and 5, in this case 6, 10, and 15, and create a counter melody, or a bass line in this case, to my melody. When you combine the 2, 3, 5 melody with the 6, 10, 15 counter melody, you get a nice counterpoint. each of these building blocks and putting them together, you get the foundation of this song.